Okay. Yeah, we're all in now. So like I was saying, these are 5 different fabrics. They all contain 15%, another 5 containing 20, another 5, 25%, 30, and then finally another 5 containing 35. Okay. And their tensile strengths have been measured. So this is a tensile strength of overall 25 fabrics. Okay, that is 5 fabrics for each of these 5 treatments. So it will be 5 times 5, which is what? 25. If you check the observation, this 1, 2, 3, 4, 5. Okay, times 5 in the column, in the row. Sorry. So we have 5, 5 will be 25 what? Observation. It means that your N, the number of observation here is what? Is 25. Okay, it's 25. Good. Then we also talked about the formula for the sum of squares. The sum of squares what? Total, okay, which we said is equal to the summation across the rows, summation across the columns, Yij, okay, meaning all elements in the row, all elements in the column, okay, squared, minus we have, that is Y naught naught, which is the summation of all the elements squared, something like this, over your N. Okay, good. So this simply means you're going to square all the, we're going to square all our observations. Okay, so if you want to find Yij, it means that when you pick row 1, okay, column 1, it will be this cell. Okay, so this cell squared, row 1, column 2 squared. So you keep squaring all the data. You have to square every single observation, okay? In the whole data set. So the entire variation in the data set, that's what we are saying. So we square everything, okay? So technically what we do is, in writing, what you do is you write this, very probably write the first 2 or 3 terms, and you use the ellipsium and then write the last terms, which will be 7 squared. Okay, 7 squared plus what? Plus 7 squared. Okay, plus dot, 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 plus what? Plus 15 squared. This is a 15 here. Okay, plus the last term, which is 11 squared. Okay, then minus, so minus Y naught naught. Y naught naught is the total of every data set you have. Okay, let me undo. So Y naught naught is the sum of the entire.
Sir, why did you omit the 9? You didn't put the 9 square.
Yeah, what I said is you can't write everything. Okay.
Okay.
Yeah, you can't write everything. The 15 here, okay, the 15 here is not for the first row. It's not for this. It's not for this. Okay. Are you with me?
Yes, sir.
It's for every data. So the 15 is this data here. I mean the last. So you write the first 2 terms, and then the last 2 terms, because you can't write the square of all 25 observations. Do you understand?
Okay.
Then minus Y naught naught. Y naught naught is the grand total. So if you want the grand total, you can first sum the total for each row. Then when you finish, you sum it across the column. So when you come here, 7 plus 7 is 14, plus 15 is what? 29, plus 11, 40. Okay, and then you do same for this row. That will be 77. Do same for the third row, fourth row, and the fifth row. Then when you are done, you sum across what? Across the rows. That will give you the Y naught naught, which is 376. So that should give us 376 over your N. Okay, don't forget there is a square there. So 376 square over the N, which is what? Which is 25. Okay, so that is how you get the sum of squares, what? Total, okay? So you find the summation Yij squared minus your Y naught naught squared over N. Okay, so this well noted. We go on to, I think I have the calculations down there. So we'll just go there and then I'll explain to you. So yeah, so like we said, you first have to do this calculation. Once it is done, okay, so I've calculated that to be a total of 636.96. Okay, if you verify, I think you also get it, but you may not have enough time to do that online. Okay. Yeah, then the next thing is to find the sum of square treatment. The sum of square treatment, like we saw from the formula earlier, is 1 over the number of replications for each group. Okay, so in this experiment, the number of replications for each group was what? Was 5. Okay, so if you come here, the number of replication here, okay, so we have 5 for each group. There are situations where you have an unbalanced design. Unbalanced design means that you can have a situation where this percentage cutting, okay, may not have all the 5 observations. Maybe you go to 35 too, you may not have all the 5 observations, okay? So this is an unbalanced design, okay? So in this design here, you cannot use this general formula we've just put out there, okay? So you cannot employ this general formula, which is 1 over n, which is 1 over 5. No, the 1 over 5 will now tend to, let's say if you have the first observation, this first data set here, yeah. So if this first data here is, let me take this, I need this. Yeah, this here is 4. And then maybe this here is 3. Okay. Then the formula will now become, for the first data is going to be 1 over 4, okay, times your yi naught. That's the total of that row, times the yi naught, which is what? Which is 49 squared, plus 1 over 5. So the 1 over 5 will apply to the row that has all the 5 observations, because the n there you are seeing is the number of replications for the treatment. So 1 over 5 times what? 77 squared, okay, plus next group has 1 over 5, okay, times what? Times 88 squared. Then the next square will be, the next group will be what? 1 over 3 times 108, plus finally, sorry, 108 squared, plus finally 1 over 5, okay, times 54 squared, okay? Then you come and subtract your y naught naught, which is a grand total all squared divided by n, okay? So then that will give you the sum of square treatment for an unbalanced design. In real life, sometimes you have unbalanced design, you understand? So like I cited from the beginning, the number of people the Americans are testing with their vaccination, okay, is different from the number of people the Chinese are testing with their vaccination. So let's say if this is coming from America, and America has tested their experiment on about 120 people, okay, or 200 people. China has tested on 90 people. And then maybe Russia has also tested on 40 people, okay? And I want to find out whether there are differences in the effects of these various vaccination, these various treatments, which are vaccination. Then when you are testing the effect, you employ an unbalanced design, because here you have, it's not the same number of people. You have 120, 90, and 40. So when you are testing, you employ an unbalanced design in the analysis, not a balanced word design. Any question?
Sir, I'm a bit lost. Is it because it's an unbalanced design that you started with the 1/4, and then I could also see 1/5 and then 1/3? I need an explanation in regards to that aspect. How you come about those stuff? Okay. Because I think the number of replications there are 5. There are 5, right? 1, 2, 3, 4, 5, and then you started with 1/4. Then at the long run, you still used 1/3, and then 1/5 again as the last one. So I'm confused. I'm a bit confused.
Okay. So what we are saying here is we change the design a bit. Okay. You see, I've erased one of the data. Can you see that?
Yes.
So I'm saying that assuming your data was like this, where for the 15% cotton, you have just 4 observations.
Okay.
And then for 30%, you have 3 observations, not 5.
Okay.
So in the case where the number of observations for all the treatment are not the same, we call it an unbalanced design. You understand?
Okay.
So if it's unbalanced design, you don't just apply the formula just as it is. No, you have to find their independent words. So now you use their replicates to multiply their row total square.
Okay.
That is what
I get it. I get it.
But in this case, in this example here, okay, like we had initially, all the replicates are the same. So we proceed to apply what? We proceed to apply the formula, okay? So it is 1/5 times the total for the various rows, okay, which is 49 squared plus. Once again, you don't need to write all of them. If it's under examination condition, you don't need to type everything. So you can type the first term plus the ellipsion ... plus the last term square, okay? Good. Minus the grand total, which is 376 square over 25, okay? So once you do that computation, we should be able to get what? 475.76, okay? So that will be the final answer. Then once you obtain the final answer, like we said, the sum of square errors, okay? It is when we talk about the sum of square error, we are talking about the errors within the treatments themselves, okay? So you see in the experiment, what we are saying is we want to check if these treatments, let's say drug A, drug B, drug C, or the levels of cotton, which is 15%, 20%, 30%, okay? Those differences amongst them, okay, between these treatments, is what is causing the tensile strength, the differences in the tensile strength. That is the whole experiment. So the differences in the treatment are resulting in the differences in the tensile strength. Okay, but when it comes to the sum of square error, we are talking about the measurement errors within the group themselves. Okay, so the errors, the variation in the data within the group A data itself, within the group B data, and then within the group C data. Okay, but you see those errors and the errors among the treatments add up to form the total error. So if you want the sum of square error, it is the sum of square total, which is the total variation minus the variation between amongst the. Okay, good. So that on that point, you should also take note that there is no way you find the sum of squares treatment greater than the sum of square total. Okay, sum of square treatment is the error just between or within the treatments. Among the treatments plus the errors within the treatments. Okay, so always your sum of square total will be bigger, will exceed the sum of square always the sum of square total will exceed the sum of squares treatment. So you take note of that. Good. And once you get it, you get the sum of square error to be 161.20. Okay, what's next? After you've calculated this, the next thing to do is to construct your ANOVA table. Okay, and in constructing the ANOVA table, like we said, the first header will be the source of variation. And then here, our variation is due to the treatment we are looking at is the percentage of cotton, okay? So the source of variation is the cotton weight percent. That is the treatment. Then the error comes in, and then we have the total. Then the next thing is you look at the sum of squares we just calculated. For the treatment, we had 475. For the total, we have 636. And then error is 163. If you add them, this plus this should give you the total, okay? Then the degrees of freedom, we said we have T minus 1, okay? The number of treatments were 5. We have 15, 20, 15%, 20%, okay? 25%, 30%, and then 35%, okay? So there were 5 treatments in all, right? So we have 5 minus 1 will give you 4, okay? Then here you have N minus T, and the total number of observations was what? Was 25. So 25 minus your treatment, which is 5, will give you 20, okay? Then for the total, you have N minus 1, so 25 minus 1 will give us 24, okay? Then once you're done, the next step is to find your mean squares error, or your mean squares, okay? So mean squares, like I told you, the MS treatment, it is given by the SS treatment, which will be what? So in calculating this, you use the sum of square treatment, which is 475.76, okay, divided by what? Divided by your degrees of freedom, which is what? Which is 4, okay? Good. Then once you calculate that, which you should be doing for me at now, then for this also is going to be 161.2, okay, divided by what? Divided by 20. So you should do the calculation for that too as well. Okay, so what favor to give us the answers? Favor, Chibo.
Yes, sir.
Yes. So what did you get for the first one?
161 points. Okay, first one, yeah, 475. 118.9.
Yeah. So you have what?
118.9 for the first one.
That's 47.
Yeah,
47 what?
475 points. Okay.
So
The
you have
answer is 118.
118.9. Okay, which is correct here. Okay, and then secondly, to when you calculate the next one, I'm sure you still get 8.06. Okay. Uh,
06.
yeah, 8.06 should be the answer. Good. Yeah, so when you're done, the next thing to do is to calculate your F statistic. The F statistic is given by your MS treatment, okay, which is what? 118.9
Yeah.
divided by your 8.06, okay? Good. And once you calculate that, it should give you 14.76. Chidi, I hope you are doing the calculation. Chidi, are you there? Chidi. Okay, Chidi is not with us. Okay. Yeah, so that should give us 14.76, okay? Then this percentile value, there is a way to compute it, okay? But like we said, we are employ the critical value approach, okay? So we're still going to stick with the critical value approach in deciding on the rejection region. Okay, yeah, okay. So what next? Then we said that we have to go and read F with alpha, and then we have what? T minus 1, and then N minus T degrees of freedom, okay? So in this case, our alpha was 0.05, 0.05, that's 5%, okay? And then your T minus 1 is what? Is 4. And your N minus T is what? Is 20. So we have to go read this value from the table, okay? Okay, so what I'm going to do is, let me create a new page and copy. I'm going to copy the table from our textbook, which is Myers and Myers, okay? The appendix of the Myers and Myers. I hope by now everybody has that book, okay? I'm sure I've been checking on that. So if you still don't have it, make sure you have the textbook with you. Okay. Now, when it comes to the reading of an F table, okay, the reading is a little bit different. You first have to check whether the F table, you see, when you come to the table, each of the tables has their own significance value. So over here, we have F with alpha 0.025. But that is not the table value we're looking for, right? We're looking for F with probability what? 0.05. So we have to go back and locate the exact F table, okay, which has the 0.05. So we go up a bit. So this is 0.10. This is not the table we're looking for. This is F 0.05, okay? So this is the table we have to come and read our data from. Oh,
So we can't see any table.
yeah.
I'm not seeing what you're doing.
I just realized I was not sharing that screen. So let me go back. Yeah, now you can see. Okay. So like I was saying, the F table has different values. Okay, so when you come to this table here, this is F. This is F at what? 0.10. That is not the table we're looking for. So we have to go down a bit. So you go to the next table. And then we realize that we now have F with probability 0.05. This is it. So this is the table we intend reading. Okay, so F with probability 0.05. This is what we're looking for. Okay, then next we have to read our degrees of freedom, which are I think 420. 420. 420 means you have, this is your V1. That's your first degree of freedom, V1. Okay, and then the second degree of freedom, V2. So here we're going to read 4. Okay, and then at this point we're going to read 20. Okay, yeah, so we read the 2 columns like we always read a statistical table. So where they intersect, this is F, the critical value. Okay, so our critical value is what? 2.87. So our critical value is 2.7. Okay, so let's go back. Okay, so what we are saying here is our critical value is 2.87. So if you plot a graph, it will look like this, which means that our rejection region is on the right of 2.87. Okay. Now, if we compare the F value we just calculated, the statistic value, when we plot it on the curve, okay, 14, let me undo this. So 14.47, when we plot it on the curve, will lie way on the right in the rejection zone, okay? Will lie way in the rejection zone. That will be 14.7 somewhere here, okay? So which suggests that at the significance of 5%, we have sufficient evidence to reject what? The null hypothesis, okay? Okay, so let me say that again. So at a significance of 5%, we have sufficient evidence to reject what? To reject the null hypothesis, okay? So we reject the null hypothesis. So if we are rejecting H naught, then what are we saying? Okay, then we are saying that there is a difference, okay? There exists some differences among the treatment means. So let me quickly go back to the hypothesis. So in the hypothesis, we are saying that what? One, all treatment means are the same, and then not all are equal. So if we've rejected a null, then we are saying that at least one of the treatment means is what? Is different, okay? Good. So if one is different, then the question that arises next is, so which one is higher, or which one is greater, and then which one is the least, okay? Once there are differences, there should be one that is higher than the rest, okay? And over there too, we have statistics which are used for the differences, for significant differences, like the LSD, least significant difference method. We have the Turkish method, Okay, we have the Bonferroni, we have the Dunettes, we have, in fact, we have so many tests, okay? So many tests which we can use. It will also depend on the type of data, okay, and the type of design at hand. Very well. So what the F statistics help us, or the ANOVA helps us to achieve, is to investigate whether there are differences in what the treatment, okay, or the effect, whether the effect of the treatment are significant, okay. Very good. So those are two types of designs, or two type experiments. The one-way analysis of variance can help us to achieve. Any question?
Sir,
Yes.
sir, I have at the p-value, is it in all cases that it's less than 0.01?
The p-value, no. When it comes here, this 0.01 you are seeing is your alpha value. Okay? Alpha value, yes. So here they are being tested as against alpha of 0.05. But like I said, there is a way to estimate the p-value too, okay? So maybe probably we'll touch on that. It's not part of the objectives though for this class, but maybe if we have enough time, I'll just touch on it. We still have experimental designs and statistical quality control to look at. Okay, any other question?
Like in an exam, there's no need writing the p-value.
No. There's no need writing this.
Okay, sir.
In an exams, no need writing this column. Okay, if you check the initial table I gave you, there's nothing like P table on it. So the table will end with your F statistic value. Are we clear?
Okay, sir.
Yeah. Any other question? Monsieur Diallo, par des questions? Is Diallo with us?
No, I don't think he's in.
Okay. I think his network is off. Okay, any question? Paul, question? Paul, do you have a question? Okay. We are not hearing from him, but he's still with us. Paul, do you have a question? Okay, he doesn't. Okay, let's. So there is a second question here. There's a second question here. Okay, now before we go on to that question, there is a very important measure, okay, which we need to look at, okay? We call something the coefficient of determination, okay? The coefficient of determination. And like we saw from linear regression, we said R squared gives us the amount of variation in the dependent variable, which is what explained by what? The independent variable. So in this case, our tensor strength, okay? The tensor strength is the dependent. It depends on the amount of cotton in the fabric. So if we are looking at an effect model, then indirectly we are trying to say that it's a kind of model like the tensor strength. Let me put it this way. Okay. So we're looking at a type of model like what? The estimated tensor strength is equal to some beta naught, okay, plus what? plus an effect beta 1, okay, and the amount of what? The percentage cut, let me put it this way, percentage what? Percentage cut, which is the independent what? Which is the independent variable, okay? So in such a model, your R squared is very important. And that R square, which is the coefficient of determination in ANOVA, is estimated using what? The sum of square treatment over the sum of square total. The sum of square treatment over the sum of square total. Okay, good. And for a more general formula, okay, for a more general formula, because sometimes the ANOVA is no more one way, we can also do a two-way analysis of what? Variation. Okay, so for a more general formula, we can also write that R squared is equals to the sum of squares, okay, treatment over, you see here we are talking about blocks. So if the blocks, the treatment, we have more than one treatment. So maybe in the case of the fertilizer, your treatments are level of water, amount of water. Okay, so we have amount of water applied, and then you have another treatment which is fertilizer, amount of fertilizer. Okay, then it means there are two different treatments. That is a two-way analysis of variance. So in such an experiment, it is the sum of square treatment in the blocks, okay, over the sum of square treatment in the blocks, the treatment plus the error, which still comes back to sum of square treatments, okay, over the sum of square total. So that gives us the R squared, okay, the amount of variation in the dependent explained by what? The predictor. You need to know this. You need to know as an engineer or as a scholar. So anytime you run analysis of variance or modeling, you always have to give us a measure of the accuracy of the model. Okay, so how accurate is that model? So indirectly, what we are saying is, if it's an effect model, then how well can your treatment, how well can it cure, okay, or how well does it predict the curing time of what? Of a disease. That can be a typical example. If you have any question, you can ask. If there's any question, you can ask.
No, sir.
Great. If you have a question, you can raise up your hand. Okay, I'll call you. So you raise up your hand. There is a button on the lower right corner. You just, Serge has his hand up. Okay, so where is Serge?
Sir.
Yes.
How do we get the SSB?
SSB here, we are talking about two-way. We've not looked at that. Okay. But in our context, SSB is the treatment.
Yeah, I know, but like where there are two cases, is it the addition of the two, like individually, the addition of the two treatments?
No. We have treatment and we have blocks. Okay, but we've not looked at that yet. It's a bit complicated than what we've done.
Okay, sir.
Yeah. And let me mention, you see, this experiment, like we said, here we are dealing with real experiments. And real experiments can be very complicated, okay? Sometimes for even this analysis of variance, one-way analysis of variance, most of the times you will have students who have conducted experiments, and then when they are defending their final viva, okay, they come and defending the final work. You realize that you don't take into consideration this knowledge. So somebody goes on